Hello, class. This is Mr. Mormon. Welcome to Nature of Science Lesson 9. Today we have a short video about density. Let's start with a definition. Density is the concentration of matter in an object. In other words, it's how well packed the matter is, how close together all the atoms and molecules are. In something that has a high density, the matter is very tightly packed together. All the atoms and molecules are very closely packed. In things that are less dense, the atoms and molecules have more space between them. They are less well packed. Another way to say this is that density is the amount of matter in a given space. Now, density is a little bit different than some of the other properties of matter that we looked at in the last video because density cannot be measured directly. You have to measure the mass and then divide it by the volume. Here's the formula for density. Density is the mass over the volume. Here's another way to think about it. Mass over volume would be the mass divided by the volume. So you need to find the mass of the object, the volume of the object, and then divide the mass by the volume, and that will give you your density. Now, the units for density are always going to be a mass over a volume. Grams per cubic centimeter, grams per milliliter. These would be the common units that we would use in class. Now remember, a cubic centimeter and a milliliter are the same volume, so these units for density would be the same as well. Grams per cubic centimeter or grams per milliliter would be the same units of density. Now, density is a physical property of matter. We can go further and say it's a characteristic property, meaning each different material is going to have its own density, and that density is going to be the same for all samples. As long as they're pure samples, they should have the same density. What I'm saying is if you have pure gold and you have pure gold that was mined in Africa or pure gold that was mined in Siberia, they're going to have the same density. All gold would have the same characteristic density. But let me show you some examples of what I mean. As I said, gold has a characteristic density of 19.3 grams per cubic centimeter. It's actually the most dense material on Earth. It's very, very dense. And all gold, if it's pure gold, would have the same density. And it's one way to identify, if you find a yellow metal and want to find out if it's gold or not, you would calculate its density. If you get 19.3 grams per cubic centimeter, guess what? You got gold. Aluminum is a metal also, but you can see it's quite a bit less dense. Water is one that we're going to be talking about quite a bit. Water has a density of 1 gram per cubic centimeter. That's the characteristic density of water. Now, a lot of students have difficulty with the concept of density. So let me try to explain it in a couple different ways so that it can make it clear. Again, think of it of how well packed the matter is. It might help to think back to a riddle that we've all heard. Remember the riddle about the bricks and the feathers, or the lead and the feathers? Which weighs more, a kilogram of bricks or a kilogram of feathers? And the answer is they each weigh the same. A kilogram is a kilogram is a kilogram. However, I think we know that the volume of feathers to equal a kilogram would be much, much greater than the volume of bricks or lead, because the feathers have a much lower density. So their volume would have to be much, much greater to equal the same kilogram because their density is much lower. The matter in the lead or the bricks is much more tightly packed, so it would take a much smaller volume to equal that same kilogram of mass. Okay, it's because of their densities. It's also important to note that density of a substance can change. As the temperature of matter increases, its density decreases. This is because as the atoms and molecules get more energy, get excited by being heated, they bang into each other more, and they all spread out a little bit, so the material becomes less dense. Think of hot air. Hot air rises because it becomes less dense. Also, as pressure increases, density increases. The matter gets compressed. It gets all the atoms and molecules get squeezed closer together. Now, in general, gases are going to be the least dense state of matter. Solids would be the most dense. Now, there is an important exception to this: ice. Ice is a solid, but we know that it is less dense than liquid water. Because ice floats on water. We're going to talk a little bit more about floating right now. Let's talk about buoyancy. Now, buoyancy is the tendency of an object to float or sink. An object will float if it is less dense than the substance it is placed in. For example, cork floats in water, but lead sinks. Cork is less dense than the water, where lead is more dense than the water, or cork. It's important to note here that buoyancy is a force that pushes up. That's very obvious with the cork because it floats. But it's also important to note that even the lead is experiencing an upward force because of the more dense water. The buoyant force is also acting on the lead. Here's a way to think about this. Very heavy objects are actually easier to lift if they're underwater. They're actually going to weigh less because of that buoyant force pushing them up. The pressure of the very dense water will be pushing up. When I say very dense, that's with, when compared to air, water is much, much more dense than air. Obviously, the lead or the rock or whatever it is that's in the water is more dense than the water, but that buoyant force will be making them feel less massive, and they will be easier to lift. Here's another interesting thing to consider about buoyancy. So here's another beaker with water in it, and I'm going to draw several things placed into that water. Now, here are the objects that I've drawn in different positions in the water. Let's recall that the density of water is 1 gram per cubic centimeter, or 1 milliliter. Now, ice has a density of approximately 9 grams per cubic centimeter. So which one of these objects, A, B, C, or D, would represent ice when placed in water? Which would you choose? A, mostly underwater, a little bit above. B is about half and half. C, mostly above the water. Or D, completely below the surface a little ways. Which would you choose? Well, the answer is A, because A is floating with about 9/10 below the surface and 1/10 above. Because ice has a density of 0.9, it's 9/10 the density of water, so it will be mostly under, with only about 10% showing above. Those of you who showed B, those of you who chose B, I can see here that B is about half in and half out. That might be how maybe pine wood would float. Pine has a density of about 0.5 grams per cubic centimeter. C is almost completely out of the water. There's only a little bit below. That might be something like styrofoam, which might have a density of 0.1. And D, because it's below the surface, D must have the same density as the water itself. An object that has the same density as water will stay wherever you put it. If you put it at the bottom, it'll stay at the bottom. If you put it right below the surface, it will stay there. That one would have this exact same density as water, which would be 1 gram per cubic centimeter. Okay, let's look at some examples from the state test now. Here's an interesting one which relates to what we just learned about buoyancy. A rock hanging from a spring scale is being lowered into a graduated cylinder containing water. Figure A shows the reading on the spring scale before the rock is lowered into the water. Figure B shows the reading on the spring scale when the rock is in the water. The reading on the spring scale in figure A is greater than the reading on the spring scale in figure B. And in 64, we need to explain why the spring scale shows a greater reading in figure A than in figure B. Well, the answer to this is, like what we said with buoyancy. The answer is buoyancy. The buoyant force from the water is pushing up on the um, rock, making it, have a lower mass. So it would be buoyancy. The buoyant force of the water pushing up on the rock makes it have a lower mass than the rock that's just hanging in air. Now, 65 is not related to what we just learned, but let's answer that one anyway. Explain why placing the rock in the water causes the water level to rise. Well, that relates to what we learned in the last lesson about displacement. The water is being displaced by the volume of the rock. And we could estimate the volume of this rock. It started at 100 before the rock was in the water. It went up to 125. Those would be milliliters. So the volume of the rock would be the difference between the two. That's about 25 milliliters or 25 cubic centimeters. Okay, here's another one. The beaker shown below contains 4 liquids of different densities. The blocks shown in the beaker represent 4 different solid materials. The table below shows the densities of 4 solid materials. Indicate where each of the 4 solid materials would be located by writing the name of each solid material in the space provided. Now, first of all, notice that these liquids here on the left-hand side are all arranged by density. And if you're very careful about pouring these liquids into a container, you can get them to separate like this. We've all seen how water and oil separate. We see corn oil and water. But these other more dense liquids will be even lower in the column, and they will separate into individual columns like this based on their density. The most dense on the bottom, the least dense at the top. So let's figure out where these materials would go. All right, copper has a very high density at 8.9 grams per cubic centimeter. So where do you think that one's going to go? Of course, that's going to be the one way on the bottom. Now, looking back at the list up here, I would probably do rubber next because it's the next most dense at 1.34 grams per cubic centimeter. That would come between the glycerol and the corn syrup, so that must be this block here. The plastic at 1.17 would go here. And finally, the wood with the lowest density, 0.71, is going to be floating above all of these. Okay, here's another one from the state test. The data table below shows 3 properties of 6 different size samples of quartz sand. One property of the samples is labeled X. A student used the data for mass and property X to calculate the density for each sand sample. Okay, question 77 asks what property of samples is represented by X? Well, there's 2 clues here to give us the answer. One, the units here they give are cubic centimeters, and those are units of volume. The other thing that would tell us that the answer is volume is that we know to calculate density, it's the mass divided by the volume from what we just learned in today's lesson. So we know this property must be volume. Okay, and for this next question, all the quartz samples should have had the same density. State one error the student may have made during the experiment. So like we said earlier, yes, all the densities should have been the same if they were pure substances, all the same. He should have gotten the same density for each one because density is a characteristic property. Some of the errors could be a human error in measuring the mass, error in measuring the volume, errors in calculation when you do the mass divided by the volume. Any one of those would have been a good answer for 78. Okay, here's another problem that has density in it from the state test. It says base your answers to 33 to 35 on the table below and on your knowledge of science. The table shows some physical properties of 4 minerals. And notice that of the physical properties, density is one of them. So which mineral is hard and has the same color and streak? When I look at the chart here, there's only two that are hard, but the one that's hard that has the same color and streak would be magnetite, black and black, hard. Okay, so next is our density problem. The volume of a sample of sulfur was measured to be 5 cubic centimeters. Based on the equation below, what is the mass of this sample? Now, to answer this, we have to go back to the chart and see that sulfur has a density of 2 grams per cubic centimeter. So if the volume was 5, the mass would have to be twice that if you were going to divide it and get a density of 2. So the answer would have to be 4, because 10 divided by 5 would give us our density of 2. Okay, this video is getting a little long, so let's look at just one more short example of the kind of things that you need to know about density. Let's just skip down here to number 78. Explain why the ice floats in the liquid water in diagram A. So we look up here, we see ice floating, and you would say something to the effect that the ice is less dense than the water. Okay, that's it for today's lesson. We'll see you tomorrow in class.